Welcome to another Monday. Yippee! Monday, week 5. Thank you very much. And that means that week 5, 6, 7 is pretty great. 3 more weeks to go. And we're in spring break. Fantastic. Because it is Monday, that means we have a lab this afternoon at our normal time, 1:55, 2 o'clock. Down at 2:55. We're going to be putting together some additional electronic circuits. That's pretty much our topic for the first half of the semester is electronic circuits. We're actually surprised we're doing pretty well at following our syllabus almost to the day as far as where we're at. So the syllabus has us talking about systems, and specifically systems that have to do with electronics. But at the same time, you guys realize that our electronics have 2 purposes. One, wouldn't it be cool if we could talk to somebody who needed to design an electronics circuit? Admittedly, electronics is a career, and you can go off and get a bachelor's, a master's, and a PhD in just electronics, and then you can go off and be a person who does that for a living for 30, 40 years. So there's lots of details to be learned. But we're just learning the basics, the important stuff, so we can sort of have a conversation with people who work with electronics, or if we want to build our own electronics. But then, because this is a systems thinking class, and we're learning pretty quickly, gosh, beginning week 5 already, that systems have a lot of things in common. What changes is what type of system we're talking about. All those crazy vocabulary words of open and closed and human-made and natural and dynamic, and whether the inputs are primarily energy or material or information. But in that real quick little 10-second description, we can pretty much compare and contrast all different types of systems. And that's something that we're pretty proud of here in ISBT. That's what we get good at, regardless of what layer you're in. Whether you're talking an advanced biochemical system, or you're talking about an advanced artificial intelligence system, if it has the word system in it, you're good to go. You should be very comfortable with it. And as you guys are learning out pretty quickly, it's very easy to add the word system to just about everything, because everything's a system, so no problem. On Friday, we were having a nice talk about the periodic table of the elements. And we were specifically talking about those elements that are known in the middle, on the other side, next to that little magenta line there that we call the semiconductors. Sometimes they're called semi-metals. But if you talk about how well these things conduct, we have the metal conductors on the left. We have the non-metal insulators on the right. And even though it's not right down the middle, it's down that weird step thing, that's where we have the semi-metals and also the semiconductors. And we specifically talked about, I picked up this, put it back, has a weird point to it. We specifically talked about element, was it 14? I don't even remember. Is it silicon 14?
Yes.
Excellent. So the fact that it's 14 really doesn't add to our story. 14 is not a very special number. But what is special about silicon, the 14th element, it has 14 protons inside, is that if you look where it's at on the periodic table, we talked about this first column being group 1, then group 2, and then move the middle, and then group 3 and group 4. We had it special being in group 4, so that this had 4 valence electrons, or 4 electrons in its outer shell. And again, we're not going to get too terribly deep into high school and first-year chemistry, but we know from chemistry classes that at least the ones that we normally talk about, the first handful of rows, those outer shell electrons, once they get to 8, then they're full. And if there's no electrons, then they're empty. Obviously, we go ahead and we change energy levels. So 4 happens to be in between or halfway on the way to 8. So that's one of the reasons why it gets to be a semi-metal right where it's at. And we said, oh, by the way, you can go ahead and you can mix this with a 3 electron in its outer shell. And welcome back over here underneath the 3s, we have gallium and we have indium. Both of those guys happen to be very popular choices for the semiconductor industry, gallium or indium. And then on the other side, if we want to add electrons and go to 5 electrons, I believe it's arsenic and antimony. Is that right? Yeah, arsenic AS and antimony SV. SV for antimony? What the hell is that? It's sort of odd. It turns out that it's sort of like, if you're a chemistry major, it's sort of like Harry Potter. You learn the Latin names for the spells. Oculus reparo, that's just the Latin name for eye repair. It turns out that the Latin name for antimony was stibium. I don't know, stibium is kind of a cool name. Why don't we call it stibium now? For whatever reason, somebody renamed it antimony. So we kept the old name SSB. So the things that are important that we're dealing with, all of these guys are considered semiconductors, silicon sort of being the one in the middle. And that's usually the one that we use the most. And then into that, we put a little bit of gallium or indium, and that's 3, in their outer shell. Or we put a little bit of arsenic or antimony, that's 5. And when we put in only 3 instead of 4, of course, it's as if we're missing a shell or missing an electron, so we usually call this p-type or positive type. And my cartoon is that little guy. That's not the international hieroglyphic for a p-type. That's my cartoon of being like an empty space in an egg crate. You buy a dozen eggs. You take all the eggs out, you get this little tiny egg cup in there, and you can put an egg in it. That's my cartoon for it. And then over here, when we have an extra electron, because it's negative, because of all the, not negative in charge, but negative extra electrons going around, typically I'll draw that as a little tiny circle, a little tiny marble with an E in the middle of it, because we are talking about electronics. So what we're talking about creating empty spaces in our semiconductor and creating filled spaces in our semiconductor, which has extra electrons for these things to run around. On Friday, we specifically talked about that guy. That is an international hieroglyphic, an international icon. It's a diode. And if I draw it that way, and I specifically put the positive on this side and the negative on this side, then that diode is reverse biased. It's facing the wrong way. The international hieroglyphic is that arrow part on the right-hand side and that wall part on the left-hand side. It's supposed to intimate or suggest that current will not flow in that direction because it's going to hit the wall before it hits the arrow. And we said if you take a look at the actual construction of the diode itself, and you look inside, it's obviously a simplification, but it's an accurate simplification. This is not fiction. This is a good description of it. We said inside here we're going to make this diode out of these 2 different types of semiconductors. And what we're going to do is we're going to put the p-type over here, and we're going to put the n-type over there. Okay, so the p-type has these spaces, the n-type has these electrons. So here's the electrons. And then over here is my cartoon of little tiny parking spaces or empty spaces for the electrons. And then if we look at this from the perspective of the electrons, then we know that's not a C, that's an E. Here's positive over here, here's negative over there. And since this is our negative terminal, we have electrons outside the diode that would love to go that way. And the idea is, the way that electronics work is that electrons don't just flow through space. That would be a spark. If we take a look at a conductive wire, like our copper wire, our cartoon for a copper wire is that the copper wire already has lots of free electrons inside the D shells. It's way down here in the 3rd row. And they're ready to sort of be moved all over the place. And if we take an electron and force it inside there on its way going positive, it bounces this guy this way, this guy knocks that way. It's sort of like a picture of all the ping pong balls inside a tube, and then out pops an electron on the other side. So the way the cartoon is, the thought is that the way conduction works is that electrons push against other electrons. If electrons just fly through empty space, it's called an electron gun or a spark. We have those. You have spark plugs inside of our engine. That's a real spark plug. Those are real electrons flying across space. Happens to ignite the gasoline vapor that's around it. But we're not talking about sparks inside the diode. So normally, electrons would not flow in this direction because there's no electrons to push against. Okay? So in this direction, if we were talking about positive current, this is my little cartoon, I put an X up there and so that the current does not flow because there is not a convenient way for the electrons to push against other electrons to hop across. It's this giant gap, it's this giant open circuit. Okay, we good? We then said on Friday, if we were to change this picture a little bit, I have plenty of room on the board, I don't need to draw it over again. If we put a P over here and we put the N over there again, and this time around we still put the diode in the wrong direction, but we put these on the International Hieroglyphic. We said that's a special diode. It's called a Zener diode. And a Zener diode is formulated, it was an invention, it's a Nobel Prize winning invention, that allows, and here's my picture of these pictures again, here's positive. Nice interlude. I mentioned before that electrons typically do not fly across gaps. They usually push against other electrons. However, a Zener diode is specially formulated such that the electrons can actually fill in these spaces. It wasn't by accident, it was by design. The scientists and engineers designed it this way that those electrons could fill up those holes. In my mind, it's sort of like building a bridge across it. So once one electron fills up, another one can push it across. It's sort of like building a bridge of electrons. And then once all of those electrons are filled up, then it will act like a wire. However, this material, this is a cartoon, this material requires a push. Okay. These electrons have to be pushed across that cavern, if you will. If we were trying to get a plank, a wooden plank, from the edge of the cavern, I'm standing in the middle of the cavern, to the other side, we have to push the plank across the gulf, if you will. And this push requires voltage. And so when our Zener electrode does not have a push, then those electrons don't normally stay inside there. And as soon as we stop pushing, those electrons come back. It's sort of like they're spring-loaded. It's not by design. They don't have real springs in there. It's all based on the electronics and the energy of this system. But what's happening is this bridge inside the material is extended while we push on it with the voltage. So until we push on it with the appropriate voltage, current does not flow because the bridge isn't extended yet. Yeah, another analogy. The Zener diode that we used inside the lab last week was a 3.9 volt Zener diode. Okay. The reason why we call it a 3.9 volt Zener diode is because you need to push on it with at least 3.9 volts before current will flow. If you don't push on it with at least 3.9 volts, and that's the number they give it. It's not a deck cut and dry. But as you start pushing with voltage, these electrons start to fill up these empty spaces, and then once they fill it up completely, then things flow. Okay? That's our Zener diode with our N and P semiconductor. Another way, or a secondary way to view this, I know I have the electrons flowing this way, I have them pictured flowing from right to left. Again, whenever we have electrons flowing from negative to positive, from left to right, current, or I, is thought of as flowing from, I said left to right, I should have said right to left. From positive to negative, it's the opposite direction. Another way to view this is looking at it from the current portion of things. And I'm going to draw it this way. V. This is height. This is 0 volts. This is, I don't know. I guess it's 3.9 volts. 3.9 volts. Okay. Another way to view this is a cartoon of what is actually happening energy-wise inside the machine, inside the diode. We literally are filling this up with electrons until there's electrons all across, and then it just turns into a wire, as long as we have 3.9 volts. Another way to view that is this way. This is 0 volts. And remember, we're using current as an analogy. Air current, water current, electron current, positive current. What if we used water as our analogy? I know I drew this over here. It looked like places for individual electrons. This time around, I'm drawing this as waves on water. This is water. Okay. The 3.9 volt Zener diode in this analogy, we're using a systems analogy, can be thought of as a dam. It's a dam that's 3.9 volts high. So if I happen to have some water over here, and I start filling it up, again, I know I'm using the word volts. We could just call this feet as well. Has anybody ever built a dam before? In a creek? I don't know, playing with that in the rain. Can you imagine what the water is doing to this dam from this direction as you fill it up on this side? Sort of pushing against it, splash against it, pushing against it. Okay. When a dam holds back water, it continues to hold it back, and you can sort of imagine from physics that it's pushing this direction while the water is sort of pushing that direction. Now, if the dam breaks, then all the water flows through. Okay, that's what normally happens with a regular diode. Okay? A regular diode will hold back the current, will hold back the actual flow of electrons until it bursts, as if it was a dam, and all of a sudden, holy crap. What happens if you're in a village below the dam when the dam breaks? Not happy? What happens to the dam when the dam breaks? Not happy? Right? The dam goes away. So, honest to goodness diodes in real electronics, if they're regular diodes and they break, they explode. They catch on fire. They smell. You go, something smells like burnt electronics, okay? Because it literally exploded. And what happened to all the other electronics downstream? They probably got burned out as well. The analogy holds. If this dam is there to protect all the villagers in the village, this sleepy village below the dam, when the dam breaks, not cool. Anybody have a surge suppressors in their room? There's a little outlets with a little white thing. That's exactly what it is. There's Zener diodes inside there so that they protect the surge. They don't want to surge electricity through your little tiny village that are known as your very, very expensive MacBook. However, a Zener diode, if I draw this guy, it is a dam, but the dam specifically has a known height. So we're following this analogy, but the analogy is true and the analogy holds. What happens when the water gets higher than 3.9 volts? Have a dam. It flows over. We cool with that? If the water gets higher than 3.9 volts, then it flows over.
And then you have to build another dam, right?
You may have to build another dam. But what this does is, this guy, this is the analogy, this guy is current. We start to have a current, okay? Before 3.9 volts, no current. There's no water flowing over the dam. Okay? But once the voltage gets higher and higher and higher and higher and gets above 3.9 volts in this cartoon, it flows over the dam. Okay? If the dam is a short dam and water's flowing over it, again, stay with me this analogy. What harm is there to the dam if water's flowing over it? It didn't burst through it and explode it. It's just flowing over it. Is the dam hurt in any way? It's a little flood control dam to hold back the water, and it only allows the water to spill over once it gets to a certain height. No? It's just, what happens if the water goes back down to where it belongs? The dam does its job? That's a Zener diode. Okay? The Zener diode is not hurt by current flowing through it after we go ahead and push through it voltage-wise. It goes ahead and lets the current flow, and then once the voltage comes back down again, it turns back off. The current turns back off. The dam, if you will, is just staying there. It's not hurt in any way. A regular diode, this is my cartoon of regular diode. Here's the water. And this guy is, I don't know, 1,000 volts. Gives you 1,000 volt protection, and then eventually it breaks or it falls off. If it falls off, if it explodes, it's not a Zener diode. It's not meant for the water to flow over it, or not meant for the current to fly over it. Inside the lab, we had a light emitting diode. It looked like this. This guy was inside this picture, and it had light going over it, and it was a 2.0 volt light emitting diode. It's also a diode. Okay. I guess I should draw it over here. This guy. 2.0 volt light emitting diode. It physically looks like this. It has like a little tiny hat on top of it. Schematically, it looks like that. This going backwards. This was the long LED that faces positive. This is the negative LED, the short LED that faces negative. Again, this is positive, this is negative. And here's the voltage. According to this, how much current flows if we're lower than 2 volts? Using the dam analogy. Nothing. I like that. Okay. If we get higher than 2 volts, then the current starts to flow. The only thing that's special, well, I won't say the only thing, it's kind of a cool special thing. The special thing about a light emitting diode is when the current flows, the damn thing lights up. It's kind of neat. When the water flows, it gives off light. And the LED comes on. And then if you go ahead and give it more voltage, and you give it more current, the LED gets brighter and brighter and brighter. Kind of a neat little thing to use as a measure of how much current is flowing. Okay? So this idea of we now have an invention in silicon, okay, that can hold back a voltage and only allow the voltage to flow when it reaches a certain value. That might be useful. One place that's useful. Let me draw this properly. What's going to look like when I'm done. 9 volt. And let's see, we have an LED there, and we'll call this test. And over here we'll call this silence. Maybe it has some spaces. It's like a Roomba almost. I'm trying to draw a round smoke detector. Everybody's seen a round smoke detector in their room or in their kitchen? It's sort of on the roof. It's like that. It usually has an LED. It's lit up. It has a little tiny battery compartment. Usually it's a little square 9 volt battery in there. And then once the 9 volt battery starts to get lower, it starts to chirp. And it says, hey, you ever had that before where it goes beep? No, like, what the hell's beeping? Oh, I need to replace the battery. Okay. The thought might be, wait a minute, if the battery's dead, how does it have enough energy to beep? Okay. It turns out that it doesn't beep when the battery's dead. It beeps when the battery is low. Okay. So what it does is you put a 9-volt battery in there. Now, I don't know how the individual machines and the manufacturers work. I'm going to go ahead and just suggest that inside here, okay, is, pick a number. Let's make it a 5-volt. Is a 5-volt Zener diode. And that the LED, the LED and the IMLO battery circuit and all the other things, the smoke detector itself only needs 5 volts. But you can't go to Walmart and buy a 5-volt battery. They don't sell them. I don't think so. You can probably find them online on Amazon, but they're not a convenient thing. So you put a 9-volt battery in there. But even though the 9-volt battery is running, what happens is this guy's a 5-volt. As long as there's at least 5 volts, then the current will flow and the machine will work. It's sort of like there's a paddle wheel on the, using a lot of analogies. As long as there's water flowing over the dam, this is happy. And eventually, as the 9-volt battery gets deader and deader and deader, it gets less than what we saw before when we buy these 9-volt batteries. They're usually around 9.1, 9.2 because they're sold a little bit high. But they're like balloons; they deflate. Now it's down to 8 volts. Now it's down to 6 volts. And eventually, once it gets below its target voltage, I'm just suggesting it's 5, this current stops flowing. There's still some voltage around, and that sort of turns on the beep circuit that says, hey, replace my value here. So this is another example of where these Zener diodes might be useful. We can build an entire circuit, build an entire village downstream of the dam that needs 5 volts. All the extra voltage just runs over the dam as extra current. That's usually limited by resistors. Okay. So the P type and the N type, those are real vocabulary words. It's not a cartoon. It's not an analogy. Putting an N and a P next to each other, they're either called PN or NP, obviously. Usually called PN junctions or PN electronics. This is sort of a cartoon of how it works, even though that's how it actually works. And then viewing it as a dam is a pretty good analogy that nothing will flow unless the water is high enough, unless the voltage is high enough, and then it will turn on. And then once it turns on, the current flows and you can use whatever you want it to use for. Okay? This afternoon, we're going to take this N and P idea and make something else, or actually use something else that is even more popular and more of an invention than the diode. The diode's very, very useful. Wires are useful, batteries are useful, voltage is useful, diodes are useful. Even better, all this cartoon stuff, all these inventions, I don't know how many Nobel Prizes we have up on the board right now, probably a handful. They're very, very important inventions. What I want to do is this. Let's draw it this way. I'm going to put N over here, and N over there, and P in the middle. But the P's go up like this. This is my cartoon. Instead of having a P and an N next to each other, I've taken 2 N's and spread them out and then put a P in the middle. Sort of like, what do they call that ice cream that's vanilla and strawberry and chocolate? Neapolitan? It looks like Neapolitan. For me, I'm all about food. It looks like Neapolitan ice cream, okay? We have N on this side, N on this side, and here's my positive, and here's my negative. So here come the electrons, and they want to go that way. Okay? When the electrons experience the N of this device, No problem. Okay? What's the problem of putting a P in the middle of this lovely block of N? How will the electrons get through the material if there's a P in the middle? Remember, there's spaces in the middle. Okay. Instead of here's the design difference. We drew the diode sort of like this. Again, I know it was a cartoon, but the cartoon actually holds. Here was the P over here. Sorry, here was the P. Here was the N. Here were the electrons. And then I drew it sort of like this. Here's the spaces. And we said, if you push hard enough, you can extend, in my mind, this sort of this plank or this bridge across that gap. Here, what we're going to do is we're going to take that N, and we're going to split it in half, but this time we're going to push from this direction. What if we pushed electrons from the top down? I don't have this is not a smart board. Maybe one of these years it will be. I'll be able to push the button and get the animation. If I'm not pushing on here, this is negative. If I'm not pushing on here, apologize for erasing. This is empty of electrons. And from what we saw with the diodes before, how much current flows when this gap is empty of electrons? Nothing. Again, whatever analogy you want to use, the drawbridge is up or the plank is not extended. There's no convenient way for the electrons to get from here to there. Okay. So if we extend this bridge sort of down, then there's a way for these guys to get across. I need to draw something better. One of these days I'm going to make a fantastic cartoon, but not today. Do it this way. Here's the design idea. There's the electrons of the N type. There's the electrons of the N type. Okay. Here's the spaces of the P type. But imagine, if you will, again going up and down, we can extend this plank, and it's wide enough, top to bottom. So while the plank is empty, nothing happens. Remember that I'm only drawing this in one dimension. Make this really, really wide. While these guys are here, let me draw a picture. Here comes our electrons. These electrons can make it across, but these can't. If I were to redraw this, let me simplify this. If we go ahead and bring the bridge even further down, then these guys can make it across. It's like I'm drawing a burrito. Everything's about food. If I go ahead and make this entire thing the whole way down, then they can all make it across. So my analogy is, instead of having the bridge extend left to right in the same direction, I'm having the bridge extend from top to bottom. Do you see that, or am I confusing everybody? It's just an analogy. We're good? We would like these electrons on this side of the device to go across this gap to the other side. But if we're pushing the plank or pushing the bridge from top to bottom, then as we push these electrons down, there's more space, more area for the electrons to flow side by side.
But can't you replace the electrons on the letter P and then just have like a whole line that just goes straight down?
This guy right here?
Yeah.
What do you want me to do? I'm sorry.
Replace them with an end that just goes straight down. Can't you like do that?
There's a specific reason why we've taken this material and we've literally put it on this side, okay? What we want to do is this. Here's the reason why. I mentioned this earlier. This device allows these electrons to get from one side of the device to the other by sort of extending this bridge in between. If we pull the bridge back, then they're stuck on this side. The wider we make the bridge by pushing this thing down, the more electrons can come across at the same time. These guys need to get across this gap. And one of the words for across from the SAT word is trans. Transatlantic flight goes across the Atlantic. A trans-Pacific flight goes across the Pacific. This is trans across this device. So the inventors of this thing called it a transistor. It's a resistor that you can adjust its, you're not adjusting its resistance. That's a variable resistor. Right. But you're adjusting how well the electrons can get across this gap by adjusting this center. Okay? It's called a transistor, and what it does is, another way to draw it is this way. This way, and this way, and again with this guy in the middle. We've been talking about electrons, because I love talking about electrons, positive, negative. If we're talking about current, when the current is, that's an I, flows this direction. The current has a source. That's easy enough. The engineers decided to call the source of current the source. This has a place for the current to leave the device. They call it a sink. Okay? Source, sink. There's a drain in the sink, but this is the sink. Okay? What this guy in the middle, they call it the gate. If the gate is open a little bit, then a little bit of current can flow through. If the gate is open a lot of it, then a lot of current can flow through. You can adjust how much current is flowing by how much you open the gate. And you control how much you're opening the gate by how much voltage is on the gate terminal of this transistor. It's this guy. I know you can't see it because you're sticking in the back. Here's the sink. It's the source. I'm sorry, I said sink. This is a faucet. It's the source. Here's the drain in the sink. The gate is this handle. So I opened it a little bit. This is now acting like a transistor. If I open the gate even more, then I get more water flowing out of it. I can turn it all the way off. Okay? So now my circuit can be in charge of allowing the current to flow up and down, high and low, and all I have to do is control the gate. Okay? Let me find some crazy analogies, because I love crazy analogies. You want to get into an amazingly awesome nightclub in New York. Why did I pick New York? We have great nightclubs in Philly, right? What's wrong with Philly? Why did I pick a nightclub? Because nightclubs have people at the door. They could be called bouncers, or they could be called, are they ever called door women? Are they always guys? Are they always doormen?
They're always usually big, huge.
Big guys, okay. What do you have to do to get into a really awesome party? Who do you have to know?
Gotta be famous or something.
But in addition to that, you have to get past the guy holding the door, guarding the door. Okay. Sometimes we call that person the gatekeeper. You have to get past the gatekeeper. You have to pay the gatekeeper, maybe just make an old cover charge. Or don't you know who I am? Or my best friend's in there. They got in. Okay. The gatekeeper is in charge of the flow of patrons in and out of this really awesome party. Okay. The gatekeeper is the person who has all of the power. Okay. little tiny one human being, as long as the system, people obey the rules and don't crash the gate, they move in and out, but only because the gatekeeper lets the gate in and out. What that does systems-wise is it allows us to have a system that can control its gate. We can have a lot of people that want to get into the club, but only those that are open to the gate are the ones that can come through. Okay? Maybe this is the entryway. Maybe the sink is into the club itself. This entire idea of there is a big source and maybe even a big sink, but the gatekeeper itself is little. I know the gatekeeper guy is usually a big guy, but still, one person, thousands of people who want to get in, a very large crowd, only one human, everyone's banging the rules, they're not writing it. A little gate can control a big flow of people. Okay? This gets us to one of our largest concepts this semester. We call it amplification. Okay? Amplification means a small gate, a small little controller, actually is in charge of affecting a much larger outcome. Hopefully the gatekeeper, the person controlling the gate, is doing their job correctly and can allow the good flow of the proper people into the party. Go back to my Walmart again. Who's the gatekeeper of the Walmart when you're ready to leave with your stuff? The checkout person. They're the gatekeepers. Okay. Now, they're not in charge of doing physical harm, but they have security because people try to shoplift, of course. But you have to go through the gatekeeper. Okay. And yeah, we've already talked about adding more gates if you want to get people through. We have gates at airports. We have gates at concerts. Okay. We have tickets to get back and forth. This is specifically called amplification, and we're going to be looking at amplification this afternoon. I'll just drop some really heavy stuff on you real quick because that's what we do. Amplification is sort of where we're going the entire semester. We talked about Henry Ford wanting to build cars, and before Henry Ford invented the assembly line, they were only making about 6 cars a day. And then we saw that after he had invented his factory, they were making about 6,000 cars a day. I think it was 2 cars a day, actually. 2 cars to 6,000 cars a day. And that way, the factory was an amplifier. As long as everybody followed the instructions that Henry Ford and his engineers wrote down for them, then they could make a lot of cars. They could control a lot of movement, but everybody had to follow the same directions. Okay? We'll be talking about this a lot this semester as far as how we amplify stuff. If we need to make more iPhones, then we have to amplify how we put these things out. We're going to be working with an amplifier in class. As this guy comes up. Hello. 1, 2, 3. There it is. So there is our breadboard. We're going to be using not a transistor this afternoon. We're going to use a series of transistors in an entire circuit. Unfortunately, and I'll be handing this out this afternoon. Unfortunately, you can't really see because it's inside here. Here's what the circuit looks like. And this will make more sense this afternoon. Anybody recognize anything electronic on that system? Resistors, yeah? These guys are resistors, okay? This is resistor number 10, R10. Anybody guess how many ohms it is? 50, 25, 7.5 kilo ohms, 4.5 kilo ohms. This is an entire electronic circuit, okay? These guys right here, with the arrow coming in, and then there's a gate there, and there's a sink. These guys are all transistors. This is a whole bunch of transistors in one huge circuit. And I'll be handing this out. We'll be going over this in class. I'm not memorizing it, I just want you to realize it's there. The transistor, a Nobel Prize for the guys at AT&T. Putting lots of transistors into a circuit on a single chip, another bunch of Nobel Prizes. Okay, it's called an integrated circuit. So this schematic, all these individual resistors and all these individual transistors, actually lives on this little chip I'm holding in my hand. That's this guy. He's tiny. Where did I get to? There he is. He's called an LM741. If I turn it on its back, I said back because it looks like a little bug. They call it a chip because it literally is a chip of silicon with those, with the areas of P and N already taken care of inside there. It has this guy has 8 pins. There's 4 pins on one side. A black marker on my finger. And 4 pins on the other side. And when you take a look at it, it looks like a little tiny chip. It looks like a little tiny bug, if you will. Okay. What's neat about this is, I'll pull this guy back out. We'll be seeing this in class today. Here's our breadboard. Remember, the top is not connected to the bottom. If you take this chip and you take those 4 legs and put it like that, now it's ready to be wired up. Okay. What we can do is we can put wires to these individual 4 little pins by putting them in any of these 4. And we can put wires to these pins on this side and putting that 4. And then we can wire into this giant circuit that's inside there. This little integrated circuit as a whole works as an amplifier. So if anybody who plays guitar, when you turn on the amplifier, that's an amplifier. If you have a component stereo system and you want to turn up the volume, even though you have your iPod, the iPod even with headphones is not very loud. You turn up the amplifier, you have this big huge sound, that's an amplifier. What it does is it takes a whole bunch of movement, a whole bunch of speakers, giant concert speakers, and has them move exactly like the little gate does. So in that way, if you're at a party and you have a giant speaker system, your iPod or your iPhone acts like the gate, and it causes the speakers to move exactly the way that the little tiny iPod requires. But it's all created by using an amplifier, which is pretty neat. So we're going to be using these little circuits this afternoon. So that's it. Bye.